In my previous videos, we talk about how to specify the formation. So in this lecture, we will talk about how to design the control algorithm to achieve such formations. In the first lecture, we specified the formation by using complete graph, specify the distance between array edges. Then in the second lecture, we know there are a particular class of graph which are rigid graphs. Then we don't need to specify array edge. We only need to specify some edge so that the shape of the graph is rigid. So to design the formation control algorithm, you can, based on the distance, then if the control algorithm is only based on distance, that will be a very challenging problem. And here we focus on a class of problem that is translational invariance formation. We know for the graph, if the graph is rigid, we only need to specify some distance between the edge E. We know a graph contains vertex side, edge side, and the distance specification. So the E may not be a complete graph corresponding to array edges, only some of the edges. Then we call C is a feasible realization. Feasible realization if the distance between Ci and Cj is equal to Dij, the distance between agent I and agent J. It holds for every edge belongs to the edge set E. Then for translational invariance formation, if the position of agent I is equal to Ci times some constant value. So the constant value tau is unknown to all agents. So if xi is equal to Ci plus tau, we know then the distance between xi and xj is Dij, because the tau is the same across the network. Then we say the formation is achieved. But initially, other agents, they may have different initial locations. Then we need to design a control algorithm for each agent so that xit and xjt, the difference between xit and xjt convert to Dij as t goes to infinity. Then how to design the control algorithm? Next, we'll make the connection between formation control and consensus control. We know at initial, for the agent xi0 and xj0, the distance may not equal Dij. Then we want to design the control algorithm. If xij is not equal to xj0, then we can define the tau it as the difference between xi0, xit to Ci. You can think of if all agents have the same displacement to this feasible realization, then the formation is achieved. So if we define tau I as xit minus kci, then if all the tau I t convert to a constant tau, let's say in Rp, then we know the formation is achieved. So then it becomes a consensus problem for tau. Then it is formation problem for xit. We have talked about so many so many consensus algorithms, and more general or more the simple case, we can pick the tau it is sum of j in agent i's neighbor. So this is defined by the edge set E. So tau jt minus tau it. So more general, we talk about, we can define tau it j from an I, then f tau it minus tau jt minus tau it. This more general form. But for simply, we can just use this simplest, the basic form. Then we know if the graph E is connected in some sense. Okay, if it's indirect graph, if it's connected, so all the tau it will convert to a constant tau. So if for direct graph, the only requirement is the graph contains a spanning aberrations. So all the tau I will convert to a constant tau. Then we can change it back to the stage form. So we know that tau I dot is same with xi dot because ci is constant. So this would be the same. So the tau I, let's use the definition, xit minus ci. So minus tau it is xit minus xit, then minus ci. So that's basically the formation algorithm. We know if the graph is connected, for an direct graph all containing spanning aberrations for direct graphs, then other edges will form the formation.